Thank you very much. I'm excited to be here. It's my second time at CERM. I'll speak on the continuation and applications of the arithmetic of power series and give you some sketch of a proof of most of these holonomy bounds. This is just a display about an intrinsic way to view these holonomy bounds, which will not be my purpose in the talk. But if you prefer these, the theory of Post's formal analytic arithmetic surfaces allows to consider some kind of gluing of a formal, like an arithmetic thickening of the complement of a compact in a closed Riemann surface, and ties the holonomy bounds to potential theory and the tools of Arakelov geometry. So the double integral in Yunqing's talk was an arithmetic self-intersection number. Instead, I will want to convey here's a simple explicit bound, not just effective, but completely explicit. In the intrinsic geometry point of view, I somehow want to think of almost functions on this formal analytic arithmetic surface in the sense that, so basically we have a gluing of kind of like a arithmetic part of the function and an analytic part, and we assume a Diophantine approximation condition instead of a gluing. So we will see how Diophantine inequalities get encoded more generally than just like the setup of irrationality measures into holonomy bounds. So the following holonomy bound, concretely, we'll read as follows. So the datum is a convergent holomorphic or convergent power series on the some neighborhood of the closed complex unit disk, mapping 0 to 0 and sufficiently large in the conformal sense. In the version for integer power series, sufficiently large means the derivative is bigger than 1 in magnitude. We have another parameter between 0 and 1, the same row from Yunqing's talk. And so the datum is for an M2-polar formal functions, a formal power series with integer coefficients. So it's a little, there are several things in this statement, but it gives you an idea of what is involved. Basically, all the ingredients in the paper Yunqing mentioned. There is a Pade approximability ingredient. It reads as follows. So for parameters D and L necessarily is at least MD. But so we suppose that we have L as an upper bound on like a function of Pade approximability for the order of vanishing at 0 of all formal auxiliary functions, which are linear combinations with polynomial coefficients of degrees less than d of our given functions. I should have a hat here. So we also suppose that the Diophantine approximation conditions in the following form. So suppose instead of having fi on the nose just pull back to a holomorphic function, suppose they can be decomposed into an analytic part, so to speak, which does pull back to a holomorphic function, and some approximation part hi whose coefficients are small in a suitable sense, and the way to quantify it is by the following inequality. So we suppose that at least the pullback of the hi are holomorphic on this smaller disk, so this is the explicit condition to capture this smallness. Then we have the following explicit upper bound on the number of our formal functions. You can see in the d to infinity limit how the previous discussion is essentially, or at least some version is captured. And there is also a version, I switched the text from here to here just by adding denominators, and there is this term from completely quantifiable as well, just from the prime number theorem. There is a effective constant for each epsilon when we have denominators. And I wanted to give you actually the proof ideas of this bound all in one page, 2 slides. Auxiliary functions, some form of the box principle or Siegel's lemma or Bose-Slopes method, maybe the simplest way to express them is as follows. So we have the auxiliary module, so we put some polynomials, undetermined coefficients of degrees less than d, coefficients in 0 to h, integers. So we have that count of this part of the evaluation module, that many inputs, And by assumption that's equal to the number of the outputs, the number of those formal functions instead, which we decompose in their Taylor series as formal function, and we capture them coefficient by coefficient. So the principle of extrapolation in some sense can be considered by the following inequality upper bound. If we can bound the individual coefficient for the difference of, so basically, if you know, suppose we have function f in the evaluation module, and I fix its coefficients in degrees less than n, then how many possibilities we have for the coefficient in degree n? So if we have this upper bound, then the following product is upper bound on the number of outputs. So we compare this. This includes the box principle, and we want to use the analytic information to, so almost analytic properties of the pullback by phi to produce such an upper bound. And how are we using that? So we have this decomposition with the analytic parts. And since we want to use complex analysis, the Cauchy coefficient estimate, Jensen, subharmonic properties, or anything like that on the boundary of the unit circle, but the functions hi do not pull back to analytic functions there. So instead, we just truncate them by polynomials of degree up to n, which of course are holomorphic, plus the higher order terms. And so we estimate pointwise the polynomial terms just by the triangle inequality with the Cauchy estimate on the contour of radius rho, where the functions are analytic. So by just by geometric progression estimate, we reach the following upper bound in terms of just estimating the integrand in this Cauchy integral by its supremum in absolute value. And so the supremum of these truncated polynomials is at most b, at most this by assumption. So this was my the condition in the statement of the theorem. And so now, for example, if we use Jensen's formula or just subharmonicity of the logarithm of holomorphic functions without zero in the disk, we get the following upper bound. That's the requisite upper bound for the leading order in degree n coefficient. C, it's a strong upper bound precisely because we suppose the derivative of phi is bigger than is large, so B, basically the estimate here in the triangle inequality is the trivial one where both these terms count equally are bounded by B. And we have the following T of phi is my notation for the Nevan linear characteristic, so the integral of log plus of the holomorphic mapping. And that can be refined ultimately to the Boss-Schauer double integral term. And so remembering that product at the beginning, where we just like slice we have that many input functions in the evaluation module, and we have that many output possibilities. And so just to want to convey in this way that the holonomy bounds are something very simple in principle. In fact, we have essentially proved them in this way because this product can be refined. This estimate was a bit something of an overkill. There are the function of successive minima. There are only MD possible vanishing orders n that are in the product. There's a lot of automatic vanishing between two successive minima. So actually the analysis refines to the following inequality. And then just taking the leading order term in it refines. So you have h to infinity. So this amounts to the following explicit inequality. This is exactly the explicit bound that I had. So it's something very simple and explicit. And in the limit that the degree goes to infinity, well, necessarily then you can see that the hi analytic terms are zero in that limit, and we recover a proof of at least some version, which is more or less the version we had in the paper on unbounded denominators property of non-convex modular forms that Yunqing mentioned, with the double Nevan characteristic on top and this arithmetic degree term on bottom. But with Arakelov theory, there is a refinement in the spirit of, I will not read out for time pressures, but it's very geometric. So basically the algebraic geometry prototype of this type of holonomy bounds with potential theory inputs is so that for any morphism of normal projective surfaces over a field, the degree of the morphism is bounded by the quotient of two self-intersection numbers. You take an ample divisor, ample curve on the target and on the domain, and this is the self-intersection of the direct image, and the proof of the prototype is an easy Hodge index inequality, that kind of classical algebraic geometry. Instead, I will focus on algebraic, for the most part, irrationality measures. So for the case of algebraic numbers, of course, irrationality is not the issue, but then we get effective irrationality measures as applications. And the method of Apery limits that Yunqing introduced supplies one such situation. We could have h of x, like for the logarithms example, and maybe we will need or want to raise it to some powers to produce more functions, and that will introduce powers of the Apery limit eta. So here's the application. Essentially, now we follow actually a proof of the holonomy bound that with irrationality term included that Yunqing stated. So if we have a sequence of rational approximations to the Apery limit, we can take this situation. They induce, of course, there is a cost to pay for raising to powers because the denominators go to q to the m, but we have on the nose the following approximations on the powers, and then with ci equals q to the I, we apply the previous situation to the following power series. I said integer coefficients. We could have denominators in the version in the variant, for example, for logarithms as the upper limit. So they and then the approximation term has small coefficients because of the good rational approximations. And in practice, so we'll have this linear differential equation. We might have, for example, 0, infinity, and two other singularities. We may think of alpha is the small but overconvergent, the beta is the boundary singularity. And often in this situation, so overconvergent could involve a choice of a path from 0 to alpha that ends up with a regular holomorphic branch at alpha. And in such a situation, we can often find a suitable conformally large analytic mapping phi. So here is how the bound in Yunqing's lecture follows. If we set rho, so rho was the smallest, the absolute value of the smallest singularity, non-zero singularity in the pre-image by under phi. And we have this L from the function of bad approximability to basically as the zero estimate in the classical theory, which in practice, in this subject of holonomic functions, using Szydlowski's lemma in the prototype, Chudnovsky, Osgood, and so we have estimates of the form md plus c, where c is a constant that depends only essentially on the degrees, on the, let's say, the deformation type of the ODE. It's explicit for regular singularities. We treat it as a constant here. And so, so this was the condition on the to capture the proximity of the approximations. We solve it. So basically, along the sequence of rational approximation P over Q, we choose the degree parameters D by solving this equation. And then in the limit D goes to infinity, we obtain the following. So we have a familiar term. So this is the limit D goes to infinity. So the rational approximations go to infinity in this non-effective version, just to give the sense of where the approximation term comes from. So there is this term, which by the equation I solved on the previous pages is the following. And this chain of inequalities turns to the holonomy bound with mu included, which I can turn around into a holonomy quotient upper bound. And in some ways, it's something very familiar to classical irrationality measures upper bound. It's Gluder because, for example, there's this coefficient we have on top now of 2. It's also, it can be improved somewhat. I should say that we have a new paper more recently from this fall on the archive called arithmetic holonomy bounds and effective Diophantine approximation, where these, at least some details of the arguments are supplied. So this is the statement that Yunqing had on her, in her talk, where there is a elision term, which is an improvement, which I don't include here, but it is positive. So the 2 is basically now the bounds are interesting mostly in asymptotic cases rather than improving non-irrationality constants. We don't have yet applications, for example, the record measure for pi, for log2, and so forth. So, but in practice, when we start taking those powers, if you have h with a denominator type, say 1n, where the tau, the growth rates of the denominators in this example is 1, we start raising to powers, the tau multiplies by the harmonic numbers because of the type basically goes, okay, it changes 1n to 1n times 1n over 2 up to 1n over k. As in the previous work on bounded denominators property, here the idea is to start with, so we look to identify asymptotic almost near misses of the holonomy bounds. This is how we started that previous paper. And now for the new method, we will use another such situation of an almost equality. So I will start with the example. If you start taking the powers of the logarithm, you started with the type 1n. The kth power has worse denominators, but so the tau of the first k power is these harmonic numbers. So that's of course log k approximately. And we have for the map phi, we can take the exponential map of growth order 1. And so here is a concrete example of the holonomy bound, which you can see all of these bounds are conditional on the positive denominator. We would need r to be bigger than k. We can choose r equal to 4k or something like that, that takes the denominator to a constant. And of course, there is no contradiction, but the situation is pretty tight. So up to the absolute constant, we have a matching of the lower and the upper bounds. So the idea now is to add an Apery limits input. So there was no assumption in this type of example, and find some kind of blending of the following. So this is what I might call a filling up example, where the holonomy bounds are tight, so with improved maps with slower growing order for Apery limits that resolve the H over convergent combination of B minus eta A. So the prototypical theorem, I think, at least in some implicit form, is in the work of Chudnovskis and Andrei. It actually follows the version of the previous discussion. So if you start with the datum phi, which is entire meromorphic of Adamar growth order G, so the quotient of two entire holomorphic functions growing at most like e to the z to the g. And then we can choose the radius, so we restrict phi to a disk of radius r. We can choose r to be arbitrarily, and comparing, so basically we derive the following upper bound for the transcendence degree over q of x of the functions with those denominators and which are analytically resolved under phi with say meromorphic pullback under phi. I can consider the holomorphic pullbacks, the proofs are the same. And so that transcendence degree is at most g, the order of the growth, times the tau, because you have polynomially many of that transcendence degree examples if you use powers up to the kth, and the tau will scale by essentially log k when you use those powers. So by extrapolating this example, and this example was the case g equals 1 and tau equals 1. And another example is from, for example, a CM elliptic curve where you have the Weierstrass P function, meromorphic of order 2, and you have vanishing P curvatures for half the primes asymptotically, so that gives you also a near miss. But this example was in Yunqing's talk in the simplest special case, and you recognize the, I think this is due to Apery, Aladi and Robinson, and Boykers in some form or the other, and gives the standard irrationality measure for log 2, already pretty decent. And what goes on in this example, of course, there are multiple ways to view it. For example, more in line with the Eichler integrals that are in our paper on the Dirichlet value. So in this baby example, you have two functions, so this one has integer coefficients, then the integral of the function, but starting the integration from this smaller singularity that makes upper limit log 2, we have canceling monodromies of the product, so we have the overconvergence. That's the quickest way to prove this example and this irrationality measure, but they come from more intrinsically and of course classically towards, they come from the hypergeometric method, so from Hermite-Pade approximations to binomial functions. So I will show you how we can continue the classical hypergeometric method multivalently with choices of map phi, which are not the disk, but in fact are highly multivalent. And in a way, we can bridge the classical hypergeometric method. For example, we can prove transcendence of pi and any logarithm with the hypergeometric method, and we can derive effective irrationality measures for high-order roots from a fixed algebraic number. So for recovering much of that classical effective Diophantine approximation on the multiplicative group, all coming down to this identity that Thue discovered for is useful for number theory. Of course, this identity is it reflects the ODE for those three parameters has those three solutions, so there must be some linear dependence. This is Siegel's take for what Thue did, summarized into one identity. We classically, so if we also the logarithm case is derived from this by like the first two like terms in the nu equals 0 Taylor series. So it's also a special case. And classically, because of the, for example, the integral representation, we know for small values of x, this term is small if we specialize the diagonal parameters n equal to m. For small x, we have fast decaying error term. So we view this as an error term. We specialize x to a suitable rational argument, and we obtain small linear forms in one and this special value for any rational exponent nu. So we will continue this example as follows. I want to take the generating function. Now there was this binomial coefficient m plus n choose m, and it is crucial to normalize it in the following way. So I just take the like the coefficients of the binomial function. Of course, the full Pade approximation is symmetrical, changing nu to minus nu, and so this is the essentially the full form. And we discover the following. Probably it's completely classical, but we would like to know how to continue and generalize this, for instance, to maybe simultaneous Pade approximations and other useful examples. So it's essentially a rational function. It's a mess of a holonomic function if I didn't normalize in this correct way, if I didn't have this binomial coefficient cleared out. It's the following. Now, if you take the diagonal of an algebraic function, or it's an almost algebraic function up to the cyclic function on top. So if you take the diagonal by Cauchy integral over a vanishing cycle, the diagonal of a rational function is algebraic. So on the m equal to n diagonal, I have found dihedral algebraic functions. I index them by this exponent nu. So they are algebraic. I'll look to specialize x. For instance, x equal to -1 will give me forms in the rth root of 2. And I view y as the holonomic coordinate, although there's some kind of duality between starting with this kind of binomial function in x. I found another holonomic function in y. Well, it is a very simple algebraic function. It's the following with singularities. So it actually has a dihedral type So three singularities, those two have ramification indices of order 2, and infinity has ramification of order r. And both the holonomy and the Galois group of this algebraic function is a dihedral group. It's essentially algebraic of dBr. And the full diagonal per degenerating function is the following combination. So in this situation, now, I apologize for the whole context of this slide. So the only line that I want to display in this, so you know about the context of Thue's hypergeometric method, I want to compare how he used the lever. So you only this displayed equation I want to comment on. So we specialize x if we want to approximate, for instance, the rth root of 2. So it was not known how to use the hypergeometric method for large R to give an effective solution, effective Diophantine type for rth root of 2 in this way. But what Thue did, he showed that there is at most one solution of the Thue equation in the following sense. If P0 over Q0 is an exceptionally good approximation to rth root of 2, we will specialize to the following number, x, which is very close to 0. Not directly at x equals to -1, as you would have liked, but to the following, which gives a commensurable rational rth root. So that we, again, obtain linear forms in 1 and the following. But from the point of view of the holonomic function, when x was very small, we have these singularities. One of them is extremely small but over-convergent, and the other one is very large. And with the Thue level, we can actually embed Thue's analysis into power series arithmetic and holonomy bounds, and read off the ineffective Thue analysis in this way. Instead, so there was the example, the first example in Baker using this nice cube root of 2, then 5 over 4 works as a Thue lever, and so on. But for large enough R, it was not clear what to do to continue this line of sub-Liouville bound. You get some kind of holonomy bound, which is not useful. It was worse than Liouville's. Now, in our dihedral algebraic functions, so we have the singularities alpha, beta, and infinity. Those two are with monodromies of order 2. And it turns out that we can find two maps depending on the singularities, call them psi and phi, one of which we have already seen in the guise of the logarithm function and its exponential function. It has order of growth 1, and it resolves analytically A and B simultaneously. So here, the situation was symmetrical in this simple example, and B was just A at the parameter minus nu. But the new input, which was not considered in Chudnovsky's, I believe, or Andrei's work on this subject, is that there is another map that resolves the overconvergent combination alone. And the eta for which, and of course, crucially, usefully, this map has growth order strictly smaller than 1, growth order 1/2. It is completely explicit. There is a certain choice that in this formula, U depends, so the U is defined up to integer multiples of pi I, but that choice corresponds to the meaning of overconvergence, so choosing the path gamma from 0 to alpha, choose a different path, and you find a different U. And crucially, the following function, as it's clear from the formula, grows like e to the square root of z. When we had asymptotic near misses, it's clear that any improvement of this kind should give results in this framework. And the map is found by certain sequence of iterations, for example, that basically, for example, if you take the polynomial z minus z squared over 4 beta ramified at beta infinity and iterate it many times, so we pulling back by this polynomial resolves beta, replaces alpha by 2 other singularities. They are again of the same type. Iterating indefinitely explains, it turns out to converge to the explicit formula that I showed. And so to conclude the main example, how can we get essentially effectivize in this example the Siegel square root exponent in Thue's theorem for the special case of binomial numbers, just by embedding the Thue hypergeometric method into multivalent holonomy bounds. So we take for a choice of parameter r, we take phi of z to be the following 1/2 order growth explicit map. And this upper bound on the effective irrationality measures that I spelled out here reads as follows, where there are periodic inputs from the convergence radii at primes dividing the exponent r. This constant is already in Siegel's paper on the binomial equation. And finally, so choosing, so this should have a positive denominator, but you see, if we didn't have, so this was the Bose-Charles growth integral term, it has square root of r, and with r we would not get any contradiction, or only another filling up. But with square root of r, we can make the following choices to subsume, to make this term positive, then k is just large enough to make this term smaller than 1. And so effectively, the bound on the effective irrationality measure is k times log of this number. So it's essentially the square root of r, just by setting x equal to -1 without using any Thue lever. And my time is up. I should stop here, and thank you very much for your attention.
Thank you, Vesselin. Do we have any questions for the speaker?
Thank you for the talk. So could you clarify the role of epsilon in one of your first slides?
It is not really, it is when you have denominators, so this was fully explicit, and here I could maybe, it's clearer to write, suppose I have, as in the definition of G function, some sequence of denominators, D1 divides D2 divides D3 and so on, nested, like this. And this is one example of LCMs to the power T. It's just the epsilon comes from using the prime number theorem estimates. But what matters is the growth rate of the denominators, the tau in Yunqing's talk, which is T.
But so the upper bound is weaker than before, right?
No, I mean the case T equals 0 gives the previous no denominators.
But it's a minus.
Yes, I mean, all the bounds have this log minus sigma. So, for instance, you have, okay, next. Oh, I made a sign error. Okay, apologies then. Yes. Okay, I didn't say what kind of constant. Yeah, it's a minus, something that's slightly negative. When d goes to infinity, this term goes away. Epsilon goes to 0, and you recover the original bounds.
All right, is there another question? Another quick question before lunch? I had one quick question actually about, so at the end you had this effective irrationality measure for the rth root of 2 that was very explicit. And this question now I guess goes back to the beginning of Yunqing's talk, but there's also, you also as a application have an effective irrationality measure for this log 1 plus 1 over n, log 1 plus 1 over n. And I was wondering, is there like a similarly explicit sort of thing? And like, what is it sensitive to? Is it sensitive to m and n? Is it sensitive to the distance from m over n to 1 or anything, any sort of similar explicit thing with the dependence there, or?
It will depend on m and n. We haven't actually computed that one. But it will be not a great, if you actually, this paper I mentioned, it's our submission for the ICM conference is 20 pages long. So the arithmetic holonomy bounds and effective Diophantine approximation has an explicit upper bound in the L2 chi, in the irrationality measure for the Dirichlet L series. And, but the main, input of this is that it allows to refine, to recover the classical effective, for example, solution of the S-unit equation in 2 variables with a high bound, because after Bombieri's work, it was known that reduces to sharp enough, like a Diophantine bounds for high order roots of arbitrary rational numbers. So the applications here are more of a asymptotic sense. So not so for the 2 logs problem, the rationality measure isn't probably very useful in itself. It's not. What it depends on, it's in some sense it can be tracked down to this explicit bound at the start. So you can see all the ingredients here. There is a Shidlovsky, 0 estimate involved. So actually, d goes to infinity. So it just amounts to but the modular lambda function involved in the proof grows incredibly fast, and that's responsible for the large constants in this bound.
Okay.
It's not what I consider interesting in this project.
Okay, thank you. Thank you. All right, are there any other questions before lunch? If not, let's thank Vesselin again.